A man named J.J. Thomson discovered the electron in 1897, and there are tons of videos about it. But most of them ignore what Thomson himself said was the motivating factor: a debate about how cathode rays move. Want to know not only how, but why electrons were discovered? Let's go.
Electricity, electricity.
First, a little background about Joseph John Thomson, JJ, on publications, to friends, and even to his own son. Thomson was born in Lancashire, England, to a middle-class bookseller. When Thomson was 14, he signed up to be an apprentice to a locomotive engineer. However, they had a long waiting list, and to fill the time, he applied to and was accepted as a freshman at Owens College. Thomson later recalled that, quote, "The authorities at Owens College thought my admission was such a scandal. I expect they feared that students would soon be coming in strollers, that they passed regulations raising the minimum age for admission, so that such a catastrophe should not happen again." While in school, Thomson's father died, and they didn't have enough money for him to get the apprenticeship. Instead, he relied on scholarships at university, ironically leading him to greater fame. In 1884, at the tender age of 28, Thomson applied to be the head of the Cavendish Research Institute. He mostly applied as a lark and was surprised as anyone to get the position. He said, quote, "I feel like a fisherman who has cast a line in an unlikely spot and hooked a fish much too heavy for him to land." Suddenly, Thomson had a lot of resources, stability, and ability to research whatever he wanted. He ended up having an uncanny ability to find new material to research. In fact, a full 8 of his research assistants and his son eventually earned Nobel Prizes. But of course, like Thomson's own Nobel Prize, that was in the future. Why did J.J. Thomson discover the electron in 1897? Well, according to his autobiography, quote, "The discovery of the electron began with an attempt to explain the discrepancy between the behavior of cathode rays under magnetic and electric forces." What did he mean by that? Well, a cathode ray, or a ray in a vacuum tube that emanates from the negative electrode, can be easily moved with a magnet. This fact gave a charismatic English chemist named William Crookes the crazy idea that the cathode ray was made of charged particles in 1879. However, 5 years later, a young German scientist named Heinrich Hertz found that he could not get the beam to move with parallel plates or with an electric field. Hertz decided that Crookes was wrong. If the cathode ray was a beam of charged particles, then it should be attracted to a positive plate and repelled from the negative plate. And Hertz decided it was some kind of new electromagnetic wave, like a new kind of ultraviolet light. Further, in 1892, Hertz accidentally discovered the cathode rays could tunnel through thin pieces of metal, which seemed like further proof that Crookes was so very wrong. Then, in December of 1895, a French physicist named Jean Perrin used a magnet to direct a cathode ray into and out of an electroscope, called a Faraday cylinder, and measured its charge. Perrin wrote, quote, "The Faraday cylinder became negatively charged when the cathode rays entered it, and only when they entered it. The cathode rays are thus charged with negative electricity." This is why J.J. Thomson was so confused. He felt that Perrin had, quote, "conclusive evidence that the rays carried a charge of negative electricity," except that, quote, Hertz had found that when they were exposed to an electric force, they were not deflected at all. What was going on? Thomson wondered if there might have been something wrong with Hertz's experiment with the two plates. Thomson knew that the cathode ray tubes that they had only work if there's a little bit of air in the tube. And Thomson wondered if the air affected the results. Through trial and error, Thomson found he could get a stronger beam by shooting it through a positive anode with a hole in it. With this system, he could evacuate the tube to a much higher degree. And if the vacuum was good enough, the cathode ray was moved by electrically charged plates just as negatively electrified particles would be. If you're wondering why the little bit of air affected it, it's because the air became ionized in the higher electric field and became conductive. The conductive air then acted like a Faraday cage, shielding the beam from the electric field. As stated before, Heinrich Hertz also found that a cathode ray could move through thin metals. How could a particle do that? Well, Thomson thought maybe particles could do that if they were moving really, really fast. But how to find how fast the cathode beam was moving? He used the fact that he could move it both with an electric field and a magnetic field to make an electromagnetic gauntlet. First, Thomson put a magnet near the ray to deflect the ray one way, and then he added charge to the plates so that the forces were balanced and the ray went in a straight line. Thomson knew that the force from the magnet depended on the charge of the particle, its speed, and the magnetic field, given the letter B. He also knew that the electric force from the plates only depended on the charge of the particle and the electric field. Since these forces were balanced, Thomson could determine the speed of the particle from the ratio of the two fields. Thomson found speeds up to 60,000 miles per hour, or up to a third of the speed of light. Thomson recalled, quote, "In all cases where the cathode rays are produced, their velocity is much greater than the velocity of any other moving body which we are acquainted." Thomson then did something even more ingenious. He removed the magnetic field. Now he had a beam of particles moving at a known speed with a single force on them. They would fall, as Thomson said, quote, "like a bullet projected horizontally with velocity v." Note that the gravitational force is much, much smaller than the electric force on such light objects, and therefore can be ignored. By measuring the distance the cathode ray went, he could determine the time they were in the tube, and by the distance they fell, Thomson could determine their acceleration. Using F equals ma, Thomson determined the ratio of the charge on the particle to the mass, or E over m. He found some very interesting results. First, no matter what he changed about the experiment, the value of E over m remained constant. Quote, "We may use any kind of substance we please for the electrodes and fill the tube with gas of any kind, and yet the value of E over m will remain the same." This was revolutionary. Thomson concluded that everything was filled with these tiny little things that he called corpuscles, but we now call electrons, and that the corpuscles in one item are exactly the same as the corpuscles in another. So for example, an oxygen molecule contains the same kind of electrons as a piece of gold. Atoms are the building blocks of matter, but inside the atoms, there are these tiny electrons that are the same for everything. The other crazy result he found was the value of E over m was enormous, about 1,700 times bigger than that for a charged hydrogen atom, which had the biggest value of E over m for anything they had found before, which meant that either these corpuscles were very, very highly charged, or they were tiny. A student of Thomson's named C.T.R. Wilson had experimented with slowly falling water droplets and found that the charge on the corpuscles were, to the accuracy of the experiment, the same as the charge on a charged hydrogen atom. Thomson therefore came to some really interesting conclusions. 1. Electrons are in everything and are well over 1,000 times smaller than even the smallest atom. 2. Benjamin Franklin thought positive objects had too much electrical fire and negative had too little. Really, positive objects have too few electrons and negative have too many. Oops! 3. Although, since Franklin, people thought current flowed from positive to negative, really the electrons are flowing the other way. When a person talks about the current that flows from positive to negative, they're talking about something that is not real. True electrical current flows from negative to positive, and that's the way the electrons move. However, by the time people believed J.J. Thomson, it was too late to change our electronics. So people just decided to stick with, quote, conventional current going the wrong way. Sorry. 4. Since electrons are tiny and in everything, but most things have a neutral charge, and because solid objects are solid, the electrons must be swimming in a sea or soup of mildly positive material, like raisins in a raisin cookie. The first 3 conclusions are still considered correct over 100 years later. The 4th theory is called the plum pudding model. It is named after a truly English dessert that they tortured people with during Christmas. It was proposed by Thomson in 1904. In 1909, a former student of Thomson's named Ernest Rutherford was experimenting with radiation and inadvertently demolished the plum pudding model in the process. However, before I can get to Thomson's gold foil experiment, I first want to talk about what was happening in France concurrent to Thomson's experiments. This is the story of how a new mother, working mostly in a converted shed, discovered and named the radium and radiation that Rutherford was experimenting with. That woman's name was Marie Sklodowska-Curie, otherwise known as Madame Curie. And her story is next time on The Lightning Tamers. Watching my video, please remember to subscribe. Please remember to give it a thumbs up. Also, if you're confused about the history of the cathode ray, I have videos about that. If you're interested in more about Heinrich Hertz, I have videos about that. I have a lot of videos. Why don't you subscribe? And then you can spend all day watching my videos. Okay, have a nice day. Please remember to put a comment. It always makes me happy. Unless your comment is, I didn't like your video. And please remember to give it a thumbs up, unless you're planning on giving it a thumbs down, in which case, skip it.